Good afternoon. My presentation will have two parts. One is more general, the other one is a bit more techy. Can you hear me? And given the audience, also given the context of the previous presentation, I will pay more time for the first part, and I will just maybe glide quickly on the techy part, it's boring tech engineering stuff. So the motivation for this talk is just to recognize that mobile network operator data, so data that are collected from the interaction between the mobile phones and the network operators, have been shown through a lot of research research work that have a potential for official statistics. That's the good news. The bad news is that there is no systematic methodology, but rather a big pile of ad hoc methods that have been developed in papers, in projects for specific case studies and data sets. There is not the level of reproducibility and portability of these methods is quite poor because they were never thought of being developed for long-lasting programs, but more often just for a one-shot project or for a publication, right? There is also rigidity, lack of evolvability, and very little, if at all, analysis of multi-operators data. And the root cause for this limitation of existing research work is that they were developed in exploratory research. And this is the job of exploration research, to try things, to show that the things are possible. But when we want to bring this into production for official statistics, we need to have a more systematic approach. And before developing a particular methodology, we need to be equipped with what I call a reference methodological framework, right? And this is what we are trying to do in Eurostat, also collaborating with some statistical office in the SNET. And the value of this work is also that while we are conducting this work specifically for MNO data, operator data, this can be inspiring also for other sources of data that have not been used traditionally by official statistics. So I'd like to give a little bit of context about official statistics and this new data. So at the moment, official statistics can be seen as different statistical domains in tourism statistics, business statistics, etc., producing statistical product from basically only two types of data: survey data and administrative registers. And statisticians somehow, both the domain-specific knowledge in the statistical domain and in the type of sources belong to the classical training programs of statisticians. Now, what's happening today is that alternative types of data are starting to be available that are relevant for official statistics. Mobile phone network data, smart meter data, satellite images. The first talk yesterday was about satellite images, if you remember, online social network data, text data. They all have something to say for official statistics. This data, the raw data, however, needs to be transformed into something that statisticians can understand and work with. So these data have to be prepared, pre-processed, and transformed. And these are what I represented with this block up here, is a transformed data. And from the point of view of the statistician up here, for instance, in one particular domain, these are transformed data is his source, And it's probably up to an expert that has some domain-specific knowledge on the source data, as an engineer or an image processing expert, that has to take care of transforming this data and reduce the complexity of this data to something that it's less complex and more, let's say, friendly to be understood and interpreted by the statisticians. So this is how we see it. The job of the statistician will then be to develop multi-source statistics for his specific domain based on more than just two types of data, taking this as a source. But the job of the person here would be to transform the raw data into something that can be used for multiple purposes. Mobile network data, MNO data are useful for tourism, for social demographic, probably also for business, right? And we need ideally to transform the raw data into something that can be then picked up by the domain expert of different domains. And this is where having a reference methodological framework come into play. So this process up to this part should be based on a systematic design or on a systematic framework. Why it is important to have a reference methodological framework? What are the meta requirements that we need to take into account in the development of a framework that would be the basis then to develop methodologies? The first dimension is the knowledge dimension. So if we go back to the previous slides, we see that we need to have different competence to interwork together. The engineer or the image processing expert, so the expert about the source, the technologies that has produced the data here, and the expert from the statistical domains that eventually will have to produce the output. So we need to, this data here and all the process around has to enable the interworking between the two domain knowledge without requiring the statisticians to become an expert of telco data in this case, or without asking an engineer to become a professional statistician, right? We don't want to have them swapping their jobs. The second important dimensions is that we have to consider that the data flow, the data process will have to span multiple institutions. For instance, some part of the processing will take place on the MNO, on the mobile network operator premises. Part of the processing can take part in the statistical office. Statistical office should be able to exchange methodology and software, maybe also use software or methodology that have been used by researchers, right? So multiple institutions are involved, and we have to take this into account when we develop a methodological framework. The other extremely important dimension to be taken into account is the temporal dimension. Different from administrative register of survey data that are somehow designed and are produced by process that do not change that quickly. Of course they change, but don't change that quickly. Most of the new data types we're talking about are produced by technological processes that are evolving incredibly fast. Think, for instance, to mobile network, how many generations of network have happened in the last 20 to 25 years, from 2G, 3G, 4G, very soon 5G. And even within each of these areas, there is a lot of change within the network infrastructure. There is a change in that operators that started to use a CDR, called detailed record. That is the most simple form of MNO data that you have in the network. We heard earlier today that already Deutsche Telekom is looking at signaling data, which is a more advanced and valuable, but also complex source also for data. So things change. Also the use case, what is required by the statisticians change. So we have to develop a process that does not only accompany a framework, excuse me, that does not only accompany the temporal evolution, but actually promote and boost it. KIT. So knowledge, institutional, and temporal, three main dimensions to have in mind when developing a methodological framework. Looks very challenging. In Italy, we say, if you have a problem, add more olive oil, meaning that olive oil is, the magic ingredient that makes everything easier. Here, stealing this concept, I would say that the magic ingredient in system design is modularity. Whatever you're doing, just be more modular than you thought. Being modular means thinking in box and thinking in terms of interfaces between the box. And this is magic, because box can be replaced without impacting to the other boxes. Box can be moved. What is inside the box is decoupled from who owns the box, right? Box can be recomposed. The content, so what's inside, is separated from the context, so what is outside. And if you are careful in designing the interface between the box, such that the interface do not change, then every box can evolve in its own. So modularity is an extremely powerful design principle, as every engineer or software architect knows. Another very important ingredient is abstraction. not to be overfit to the particular use case, to the particular data set, to what you have to do now, but try to make an abstraction, try to distill what is common, what is common across different possible projects. I will come back to this in a second. So when you think in terms of modularity, very often you end up thinking in terms of layers. And we being telco engineers and having studied how the internet works, have a mental bias towards this hourglass model. That is actually the design principle of the internet. And the internet, like the official statistics world, is pretty much about different institutions having different infrastructure that are juggling data. So there is a lot of similarities. And we think that the layering and hourglass model can be also relevant to the design of the methodological framework. In that we have the lower layer, we have source data that are very heterogeneous across different operators. You have different operators. You have data that change over time. So here you have heterogeneity, multiplicity, complexity, variability. And at the upper layer, you have the statisticians that also have, have to serve different domains, heterogeneity. You have different statistical offices or institutions that have to extract different types of statistics. They also are complex, use complex methods in their domain, and their methods are also subject to change over time. So also up, you have heterogeneity, multiplicity, complexity, and variability. And the key to have these two words interacting together is trying to put an intermediate layer that is simple, static, parsimonious, in that it has not so much complexity, is informative but not complex, is not subject to change that fast, etc. And this is the hourglass model because there is a complexity reduction in the width of the hourglass. If we manage to do this, so this basically acts as an interface between multiple players on the bottom and multiple players on the top. And this is how we see, for instance, the whole process. We see on the D layer, on the data layer, different types of source data for MNO data. We will come back to this in a second, that have to be transformed by engineers into C layer, convergence layer structures that hopefully are very few structures, very simple to understand for the expert of both sides. And these are called the D2C mapping functions. And then the statisticians will develop C2S. So from the convergence layer to the statistics layer function to take this as a simple structure and to elaborate with more complex algorithms. So D2C and C2S, we are decoupling the two words. That's how we see it. The benefit of layering is basically, and having a convergence layer is basically putting an interface. And when you put an interface, you decouple what is at the two sides of the interface, and you allow them to evolve separately. Okay? Another key point that I would like to put forward is the separation that should be very clear between the design phase and the execution phase. Execution means production, live production, continuous production. Design means research, doing research and understand getting familiar, developing the methodology. For software, this is like writing the source code and running the binary code. So it's like execution. And we have to consider these two phases quite separate. So the hourglass model that I'm referring to is mostly directed and organizing the design. No, 10. The design phase, not necessarily the execution. So the idea is that you can put a threshold on the execution, and you can have the bottom part being executed at the MNO, and the upper part being executed by the NSI. So the benefit of modularity is that who designs a box or a part is not necessarily the ones that has to run it and operate. So there will be some part of the workflow that are maybe designed by the statisticians, but are executed at the premises of the MNO, for instance, for privacy or confidential reasons. And if we want, as we heard previously, to fuse this data with external data sources like maps or other source, we would do this at these layers. So this separation between design and execution is also propedeutic towards a model where instead of having the statistical system ingesting all the data, maybe for this new data source, we should look at paradigms where we move the computation out. So as Baldur said yesterday, bring the algorithm to the data rather than the data to the algorithm. And this also plays well with the privacy-preserving computation techniques. In this sense, it's harmonized with what Baldur was referring in his yesterday. If we manage to have this convergence layer here, then we will have the different operators. If the different operators are able to transform their data into something that is uniform, right, and can be used by the users of the data up there, we are basically building a substratum for the user to exchange code, to exchange methodologies. So we are creating not only a marketplace of data, but also a marketplace of methods, of processing up there. So now there are some more technical part of what these two mapping functions should look like, which I can skip. And whatever I have said so far can be applied without much change to any source of data. So this, for instance, the D2C, the lower function for satellite image, will have some object recognition, probably, right? Some algorithm. Now, if we have to very quickly go into the something specific for MNO data, this slide shows that every line here is a different type of data that can be extracted from the network. Most of the research has been used CDR, so-called data record, that are on this side. They're very easy to extract for the operator and relatively simple to interpret by even non-experts. But more informative data sources exist that are called signaling data. So if we put in the data in this plan, where we have the cost of extraction, the cost of interpretation here, and the cost and informativeness of the data here, I would say that the CDR and the signaling go, the signaling data have more pain but more gain. So it's more difficult to extract and interpret, but also more informative. But also you have to mix this data with data about the topology of the network. And again, you can use simply the location of the tower, but you can use also more informative data about radio propagation, radio configuration details. And the more you move in this direction, your methods will be more complex, but also more informative. And we are at the stage where many operators are already here. So our framework has to cope with all this variability in source data and also promote the moving operators from a trivial combination of CDR and tower locations towards more complex data. A key point here, a level of abstraction, is to recognize that whatever type of data you are using from the mobile network, you are not able to measure the actual trajectory of the users, but you can also only capture at some time, some location where the users are likely to be. And this location, which we call C location, is the better data you are using and the more effort you put on the lower layer, the smaller this location will be. And the more frequent in time you will have your observations. So you have to educate. We have to educate the statistician to work on data that looks like this, looks like an out-of-focus image of what they would like to see. This is not a noisy image, it's an out-of-focus, it's a different. And then there is a lot of technical stuff to show that I'm working on it, right? So the meta message is that it's really complex. I'm really clever that I can do all this stuff, right? And we are also developing example workflow. So for instance, density estimation was mentioned before by the colleagues in Tartu. There are many ways of doing density estimation, and we're trying to provide a framework where the most simple, sometimes even naive ways, and the more clever and the more advanced way are all part of, or a single framework, And for instance, two key points in this framework are the geolocation of the events, so what we call spatial mapping, and the methods that you use to do the inference of the method, of the statistical inference. So spatial mapping happens from the raw event. You have to determine the sea location, and this can be very simply a Voronoi polygon, as most researchers have done, but there are much more, let's say, advanced and informative ways of defining the sea location, and then there are different ways to do a density map. So what we are doing in Eurostat is not only to segment this methodology into structure, into box, but also to compare, especially for this part and for this part, different options in a systematic way. And to this end, we have a collaboration with Proximus, which is a mobile network operator in Belgium. Our small project with them is a very small project, a few months, is targeting the building of a benchmark data set that we can use to compare these different methodologies, right? And these are they're listed here. So if you go from 1 to 4, they become more and more advanced and less popular in the research. But also understand what it takes to suck the most informative data from the network of the operator, which was not optimized to deliver this data, right? So it's also a hands-on learning. So I'm not going to present results. We were hoping to have final results by today, but the work is still in progress. I have to say that the preliminary results that we are looking at are very much in line with what we expected. The 90% of the work are based on methodologies that are very simplistic. And there is room with a very little effort to do something much more clever, right? An additional lesson that we learned by interacting with the mobile operator is that both the statistical office like Eurostat and the Proximus in this case, we are improving our, let's say, mutual trust, but especially the operators is recognizing that while working with them, they are improving a lot their own methodology, because it's an operator that uses this data to sell analytics, to sell some commercial products. And interacting with us, they are learning, they are improving. So the more we collaborate, the more they are eager to continue the collaboration, right? And we are also learning what it takes to develop this data from there. So there is a knowledge transfer in both directions. And this is also my message to those of you that happen to work with telecoms, right? If you move away from the simplistic methodologies that are only, let's say, worth a paper, an academic career, and you start doing the real thing, they will appreciate, they will understand you, and they will be more eager to work with you. In France, the INSEE had the same experience with another operator there. So we have to scale up the official statistics to be serious with MNO data. So this is the take-home message, is that let researchers develop methodology and publish paper that shows that interesting stuff can be extracted from the data, but when we want to bring this into the official statistic world, we have to start with the architecting, with the systematic approach to develop frameworks. This is the technical framework, is also the basis to discuss business models, privacy, data governance. So there is a lot of implications on a non-technical level of how you organize the technical aspects. For instance, whether you suck the data or you move the algorithm is a technical decision that have a lot of non-technical strategic implications. The other lessons learned is that statisticians don't have to become engineers, but statisticians don't have to ignore engineers. Right? Would you trust the research done by a data scientist on genetic data that have never dared to take a coffee with the biologist? So why you trust the research that is done by statisticians that have never dared to talk to a telco engineer based on MNO data? developing reference methodological framework is the basis to develop then to implement methodologies. And this is reference methodological framework is something that official statistics have to do it, not the researchers. But if we have a reference methodological framework, maybe the researcher can develop along the lines of the framework, and what they deliver will be more usable and more readily to be brought into production. So there is also a benefit for them. And perhaps what I was saying for MNO data can be applied, much of it can be applied to smart meter data, satellite images, text, etc. And I thank you for your attention.